This lesson is going to talk a little bit about electromagnetism. There's not as much math in this section in one sense, but it's kind of more explaining what happens. And there's some really interesting stuff here. There is a little bit of math at the end, so do make sure you get to the last 3 slides. The first little bit is just kind of where it's applied and what it's useful and how it works. So electromagnetism, what is it? Well, electromagnetism was discovered when people found that running current through a wire caused a compass to deflect. So that's what the simulation is giving us. And by changing current, so just opening and closing a switch, they could get a compass to deflect, which meant there must be a magnetic field occurring. And how magnets and electricity can interact is really how a lot of different components in electrical components work, including motors, generators, transformers, and we're going to look at a couple of those. So this is just kind of more a little bit of a theory section. All right, so in this example, we have current from a battery causing a magnet. Okay, it's causing a magnetic field. Faraday discovered, well, if we take a magnet and we move it through wire, so specifically they've used a coil of wire that gives us more wire, so they move it inside of a core, the changing magnetic field, so it starts out north and then it goes to south here, so the fact that it has to keep moving, can't be stationary, he found you could actually cause a current to occur. So I think we can probably look at this and go, if we have a magnet, you know, magnets will always line up so that the north lines up with the south. If we can change a magnetic field, they said, oh, well, could we use that to make something turn, or could we turn a magnet to generate current? And that was how the electric motor was discovered. Now I know, okay, you're auto mechanics, you're dealing with gas motors, but as we get electric cars, we're going to see more of this kind of electric components. And even in your gas car, you use an electric starter. So your electric starters would be based off some of these principles. So that's the 2 main things. First one, if you have a current and you pass it through a wire, usually we use coils so that we have more wire, it will cause a magnetic field. If you take a magnet and you move it through a coil of wire, you can cause a current. So those are our 2. We call this induction because it's an induced current. It's a current that's created by the magnetic field. So where is that useful? One of the places you use it is in a solenoid. So we have a battery hooked up to a coil of wire. And what happens in a solenoid is we put a metal core inside. When we put that metal core inside, the magnetic field is represented by the pink lines. The magnetic field lines up inside the metal core. Well, you know what happens to magnets. Magnets want to attract, and that can allow us to adjust that metal core inside to close a switch, which I think you guys have probably looked at solenoids a little bit. If you haven't, I know that's one of those things that when the starter went in one of our vehicles, it was a solenoid. Solenoids are often involved in starters to help transfer electricity. So it's a switch. Once the switch is closed, electricity can travel to another location. So solenoids are fairly common to see. I actually have a couple examples in my electric kit if you happen to want to see one and see it kind of taken apart in the coil and everything, but they're kind of cool. So that's one use. We can also use this to magnetize a piece of metal. So let's say you have a screwdriver and you want to make it magnetic. Take a coil of wire, wrap a coil of wire around it, attach a battery to it, and it will actually magnetize the screwdriver. So that's how a magnetizer works. A demagnetizer would misalign that field. All right. So what about in motors? Well, in motors, we use this principle. This is for an electric motor. So you have a battery and it's connected to a terminal here. And then there's an electromagnet at this point. So this is our electromagnet. You have current going through this coil, which causes magnetism. And then it causes these poles to change. And then outside of that, you put a permanent magnet. Well, we know that the south end is going to want to attract the north. So that's going to mean that this piece here, the metal core inside, is going to want to turn to line up with the north. Okay? Now, okay, but once it's lined up, how do we keep it turning? Well, there's these brushes. well, I see lots of things with brushless motors. That's kind of the new thing. But brushes, what they do is they have little brakes and they allow the current to be basically released so that the turn can keep occurring. So it releases the current that allows the magnetic field to change, and then as it turns, it connects again, which causes a magnetic field, and that causes a constant rotation. So it's actually kind of cool how these work. But yeah, if we had a magnet, we could easily create a little motor. And I've done this sometimes just using a simple coil of wire and a battery and a magnet on a table. You can actually get rotation to occur just by doing something like this. The little, and to simulate brushes, you leave insulator on half of your wire that makes your coil, and it's actually a cool little experiment. If you want instructions to give it a shot, I can send you instructions for that. But yeah, so as this turns, this would cause this, as the current causes the magnet to change its poles, you'll have this shaft turn. And as that shaft turns, that causes other things to turn, which allows us to take electrical energy and convert it to mechanical energy. Okay, and this is kind of gives you your little textbook explanation. All right, and if the current happens to be switched, if you flip the current around, you will find the magnetic field will reverse and will actually cause movement to go in the other direction, which is kind of cool. It's actually rather cool. All right, so what about electromagnetism and generators? So we can use electricity to cause motion. What if we use motion to make electricity? Electric cars, a lot of the hybrid electrics will charge as you drive. And the charging as you drive takes the mechanical energy from the wheels that are already turning, and they use it to generate electricity to recharge your battery. So that's exactly what happens here is instead what we do is we turn the magnet. So we turn this electromagnet inside of this larger electric field. Because that's causing the magnet to move, it generates electricity, and that's how a generator functions, a mechanical generator. Another piece. So I'm going to look at a transformer and we're going to look at a starter coil. Okay, so transformer is just two solenoids. So we take two coils of wire and we bring them close to each other and we see what happens. And this is kind of, we don't have to have motion happen when we have this. So we apply an alternating current. Alternating current is just current that can change directions, or current that varies. So your motor current could be one of those scenarios, okay? So we have a current that's changing, and as that current changes, it creates an electromagnetic field over here. Now, electromagnetic fields, they fan out. So because it fans out, it's not just going to stay in this coil, it's going to expand. And if I could bring a second coil close enough, not actually touching, but just bring it close, that means that I create an electromagnetic field in this coil. Now notice, this one's not connected to power source, okay? This one's not connected to a power source, it's separate. And I have another picture that might show that better. And what happens is as this magnet in here, this magnet that we create by putting electricity through, as it changes, it creates a change in magnetism over here, which makes electricity on the second coil. So it's actually really cool. So we can use the number of coils will let us change how much current and voltage there is, but the power on each side is always going to be the same. So we won't lose any power, assuming it's 100% efficient, but we can change voltage and current just by changing the number of coils. So here's an example here. You'll notice the two circuits, they don't touch. So this one is coming from the battery. So this is the primary circuit. So this is what comes from your battery. Here's a secondary circuit that's lighting something else up. And what they do is they often will put a metal core inside. What that metal core is, metal likes to magnetize. So it concentrates the magnetic field to make it more efficient. It would be less efficient. And P is just the number of turns on the primary, so the number of turns here, and S is the number of turns on the secondary. This allows us to change the voltage and current. So maybe I want to decrease voltage to protect something. You can have that happen. Maybe I want to decrease the current to cause protection. Or maybe I need to increase voltage. So in the case of starting a car, you have a 12-volt battery. A 12-volt battery isn't enough to generate spark usually. But if you had a 20,000-volt battery, you're definitely going to get some spark. So we're going to use the principle of a transformer in order to generate a starter. So, or your ignition coil. So here, we got our ignition coil, a picture of an ignition coil here, and I'm going to kind of explain how that works. So what you have your primary terminals here. So these terminals are going to have electricity coming from your battery into them. And then here we have a primary coil. You'll notice there's a lot of coils. So we have electricity going into this primary coil. It never touches the secondary coil that's wrapped around an iron core. So this is electricity coming in. There's a lot more turns on the wire on the other side. And what that allows us to do is it allows us to create a much higher voltage. And when our voltage gets high enough, we can get output. A very high output gives us spark, which allows us to ignite the gasoline, which allows our engine to function. So that's my layman version of how one of the places where transformers apply in ignitions. Now we're going to do a couple of calculations. So there's a couple formulas that we use. There's actually 3 formulas, and I've used E instead of V. If you want to switch and use V, that's okay. So P stands for primary. That's from the source or from the battery or the plug side. And then S is secondary. That's where the power is going, the induced current's going. So you'll notice this ratio is set up just like a direct ratio. So you'll notice the first one, this relinks voltage and the number of turns. This is a direct relationship. You'll notice direct, it's set up like 2 division problems. We did this last semester, which means as voltage increases, turns has to increase. Okay? So if you want to make something have more voltage, you put more turns on the secondary coil. So the coil over here, we'd have to make more turns on it. Now, if we look down here, this one is current in turns, and you'll notice how it's set up. It is indirect. Okay? In order for this equation to be true, if you increase the number of turns on the secondary coil, the current on the secondary coil would have to decrease. So if turns goes up, the current goes down. Right? So your battery has low voltage but a lot of amps. That means it's powerful. Low voltage but a lot of amps will allow us to turn that into high voltage with less amps. And that's going to allow us to cause our ignition spark. One thing to notice is the power in is always equal to the power out. That will always be true. Okay, and that lets us kind of check and do some troubleshooting to figure out what voltages are on each side. So we're going to do just a couple calculations, not too bad. I'm going to hide the video here just because I want you to be able to see the formulas that I have up at the top bar here. So you'll notice we have our plug here. So this is our source. So this is in or primary. And this is going to be secondary. Now we can do some math prediction here. You'll see there's less coils on this side than there are on this side. We know if we increase the number of coils, we're going to increase the voltage. So let's see by how much does that happen. So we're going to fill in our chart. So if it's going to be step up because we increase voltage, it's got more turns. Let's figure it out. So 120 volts, we have 30 coils and 20 amps. And over here we have 600 coils. Okay. So at this point, we could calculate voltage or current or power. We can calculate a few things. So I'm going to calculate the power on this side first, just because I know I can fill in this last piece. So power is E times R, or E times I rather, which is going to be 120 times 20, which is equal to 2040 watts. Power is the same for both sides, so we can put that in over here. So that let us calculate two things easily. Let's do voltage first. And we'll use our formula. We can use this formula, which is easy cross multiplication and division. So 120 volts in, and then there's 30 turns on that side, is equal to X volts and 600 turns. So in order to cross multiply, you're going to have 30X equals 120 times 600, and then divide by 30. X is equal to 2400 volts. What about the current? So if you do current, well, we can use the other formula. We'll use this one. So the turns, we have 30 turns times 20 amps is equal to 600 turns times X amps. Divide both by 600. And X is equal to 1. 620 times 30 gives me 600 divided by 600. 1 amp. That's an easy way to fill out our chart. I'm going to show you a couple of things. 30 times 20 gives me 600. Voltage times 20 gives me 240. How do I go from 1 to 20? I end up dividing by 20. And 20 is the rate, is just the ratio simplified of the number of coils. So if you have 20 times as many coils, you're going to have 20 times the voltage, but you will have a decrease in current by 20 times. That's where our divide by 20 comes from. So that's just kind of one of those extra little tidbits. You'll notice these two, voltage and current, are always opposite. We'll do one more calculation and then that finishes us off. So a transformer has an input voltage, that's the first one, of 220 VAC, just means volts of AC. So 220 volts and 30 amps. The secondary has 5,000 coils and 1.5 amps. How many turns are on the primary? What's the voltage at the secondary? I find this chart is really helpful for us to figure out. So we need to find this number and this number. And in order to do that, the linking piece is, well, I shouldn't say, you don't have to calculate power, but it's often easier to do with calculating power. Let's figure out first the number of coils on the primary. So the number on the primary times, so we're going to use this formula, the current on the primary, which is 30, is equal to the number of coils on the secondary, which is 5,000, times 1.5. We're going to divide both sides by 30. And the number on the primary happens to be equal to, pull my chart out here, 250 turns. Okay. What about, so now that you have this, you can easily calculate what the voltage is, or we can calculate voltage without having the number of turns. There's two ways to do it. So we could first calculate, well, how much power is there? And using power, we can calculate secondary voltage. So I'm going to do that just as a reminder. So 220 times 30 gives us power on the primary of 6,600 watts. So to do that, I did 220 times 30. Well, we know that it's equal on both sides. So if I want to know voltage, voltage is equal to power divided by current, which is equal to 660 over 1.5, which will leave us with a voltage of 440. I got that right. Just let me do a quick math check here. Yes, I left a zero off when I wrote my notes. And that's as easy as it is. So you're just kind of working through the pieces. How are they each connected? You won't have a lot of transformer info, but just a little bit. I always like to cover a little bit of that. And it's a really good example of practicing some ratio math. And that finishes off all of our electrical. So that has us ready to do your final assessment. So that will let you finish up this unit.